Hi there, Mr. Holcomb here with another episode of The Math Behind the Modules. Hi there, lesson 22 here, comparing quadratic, square root, and cube root functions represented in different ways. Alrighty, so let's jump right in here. Classwork opening exercise. Populate the table on the right with values from the graph. So all you need to do in this problem here is find points that are on, I say, corners of the grid that give us x integers and y integers. Alright, so the first thing I'm going to plot is the vertex, and notice there are 5 positions here. I always like to put the vertex in the middle and choose a couple of points on either side, and my vertex is at the x value -2, so my axis of symmetry is x equals -2. So there's the vertex, the minimum on that axis of symmetry, -2. The y value at that point is -1. So there's my vertex. Okay, and then I work 2 points on either side. So then if I come over here, I'm looking for an integer. Well, there's definitely an integer here. That is a root. That is a solution. And that is -3, and y is 0. And then if I go the other way, here is -1, 0. All right, so continuing to the right, then I find my y-intercept right here. That is the point 3. 0, 3. So origin over 0 up 3, that is the y-intercept. And then if I go over the other direction, I'm coming up here, I hit an integer x and y right there, and that is -4, 3. Okay, so that was just a quick lesson review of finding points on a function graph. Okay, page 2 brings us to the exploratory challenges 1 through 3. It says to solve each problem and show or explain how you found your answers. Xavier and Charlize each threw a baseball straight up into the air. The relationship between the height, distance from the ground in feet, of Charlize's ball with respect to the time since it was thrown in seconds is given by the function s of t equals -16t squared plus 79t plus 6. The graph of the height as a function of time, Xavier's ball, is represented below. So Xavier's is the graph, and Charlize is the function. So we're comparing this function to this graph. Okay, so it says Xavier claims that his ball went higher than Charlize's. Charlize disagrees. So this is the graph of the ball. So Charlize is standing here, and she threw the ball from 6 feet up in the air. So say she's 5 feet tall, and her arm extended up to a 6-foot point where she let go of the ball. That would be right here, and then the ball flew up into the air, and it got to this point right here, which is the vertex, and that is the maximum. The maximum at the vertex was 75 feet. So Charlize threw the ball up in the air 75 feet. Xavier, I'm sorry, not Charlize. What am I doing? Xavier threw the ball up into the air 75 feet. Let's change that to red. All right, Charlize is this equation. So now I have to find the maximum of this. Well, in order to find the maximum of a function in this form, there's 2 ways to do it. You could do -b over 2a and then find the value y of that x value. That's the vertex. Or you can put it in completing the square vertex form, which is what I'll do. So the next step is you take s of t equals, and you group the variable terms, -16t squared plus 79t. You group those together, and you leave the constant outside. You then factor if possible. So it would be s of t equals -16 parentheses t squared plus 79 divided by 16. Actually, that's minus, right? A negative times a negative is positive, so that's going to be minus right here. Oops. T plus 6. Okay, so I factored out a negative 16. A negative times a negative is positive. These 16s would cancel and give me 79 back. And the t squared times negative 16 is negative 16t squared. So there's the first step. And then we take half of b and square it. So it's going to look like this. So half of 79 sixteenths is 79 32nds squared. And that's going to create a mess. So keep in mind that when we don't have to show all of our work. Actually, we do. I'm going to keep going. Disregard that. So let me get my calculator because these are strange numbers. Okay, so I take 79 divided by 16. And then I divide it by 2. And then I square it. And I put it into a fraction form. Okay, 6241 over 1024, or 6.094. All right. Let me leave it as 6.09. So that would be plus 6.09 plus 6. But then we have to, since we added, I was running out of room here. Since we added 6.09 inside, I have to multiply that by a negative 16. Times negative 16 is a negative 6241 over 64. I want a decimal for this. And it doesn't go into a decimal. Okay, so I took away, that's the negative 16 times the 6.09. So I'm taking away 6241 over 64, so I have to add that 2. So I'm going to multiply that by negative 1 just to make it positive. And then I'm going to add 6 to it. I don't want a fraction. 6625 divided by 64 is a decimal of 103.5. Let's just round that to 103.5. All right. So that's going to change this 6 to 103.5 because I've already figured in the 6. So it's going to be 103.5. Okay, so finally I get S of t equals negative 16 parentheses t, and remember it's going to be this divided by 2, and it's positive. No, it's negative, that's right. It is negative. So it's going to be negative 79 32nds squared plus 103.5. Okay, finally there's our vertex form. So x is 79 32nds and y is 103.5. Okay. So Xavier threw the ball up in the air 75 feet, and Shirlise threw her ball up into the air 103.5 feet. That's the y value of the vertex. So who is right? Shirlise is right. So here's the explanation. Okay, so you'd say Shirlise is right. Xavier's ball went 75 feet in the air at its highest point based on the maximum point of the graph, which was lower than Shirlise's. The maximum height of her ball is approximately 103.5 feet. And it was determined by completing the square using the vertex formula to find the vertex, or using a table to approximate. All right, so there you have it. B says, for how long was each baseball airborne. Okay, so if you look at Xavier's graph, he's standing here, this is time 0. He throws the ball up into the air and it gets to the maximum point right here at 2 seconds. And then the ball drops a little more than 2 seconds, actually, it's just a hair over 2. And then the ball drops, and the other 0 or root x-intercept is a little bit more than 4 seconds. Okay, so we can do the same with Charlize. Well, her vertex x value was 79/30 seconds. So if I take 79 divided by 32, that is 2.46 seconds to get to the maximum, and that's half the time. It takes half the time to get to the max, and then approximately half the time to come back down, and that will be our y-intercept, or x-intercept, I'm sorry. So I multiply that by 2, and I get approximately 4.93, or right around 5 seconds. So her graph would come down, and her maximum, of course, is way up here. So hers is coming down like so, and it's going to come down like that. For how long was each ball airborne? His was airborne a little bit more than 4 seconds, and hers was airborne approximately 5 seconds. Okay, page 3 brings us to part C of the question, and it says to construct a graph of Charlize's throw as a function of time on the same set of axes as the graph of Xavier's, and use the graph to support your answers to part A and B. So if I go back to graph this, I need the y-intercept, and this is her function right here, and the y-intercept is 6 feet. So that's the first thing I'm going to plot. So I will plot a point at 6 feet. Well, 12.5 is here. 6.25 would be centered, so just a little bit lower. So her y-intercept is 6 feet right there. And then I go back, and the maximum was 103.5 feet by our vertex form, and it occurred in my calculator at 2.46875 seconds, so almost 2.5 seconds, 103.5 feet, so approximately right here. And then it came down, and right around 5 seconds it hit the ground again. So there's our 3 points we're going to use to graph, and I've already drawn the graph, so I'll just swing this over here and run it through those points as close as I can. So there's approximately what her graph would look like. And so does that justify our answers from part A? Did her ball go higher? The answer is yes. And part B, how long was each ball airborne? This one was airborne a little more than 4 seconds. This one was airborne approximately 5 seconds. Okay, so moving on to part 2. It says, in science class, students constructed pendulums of various lengths. Then recorded the time required for the pendulum to complete a full oscillation out and back. The results are displayed in the table shown below. Jack looks at the first 3 rows of the table and says that a linear function should be used to model the data. Based on the data, do you agree with him? Justify your reasoning. So we have to either say yes or no to his justification that this is linear. First thing I look at are x values. Are they increasing evenly the first 3? 5, 10, 15. They go up by 5, up by 5. So yes. The next thing is how many seconds elapsed from 1 to 2 and 0.45 to 0.6. The difference is 0.15. To get from 0.60 to 0.75 was again 0.15. So it looks linear so far, but then when we get to 0.75 to 0.88, we see that it went 0.13. So at that point there, the common difference is not common, and therefore this is not a linear function. Okay. So for the first 3 rows, it does look linear, so I understand what he was looking at. Rate of change was 0.15, but then the rate of change changed. Okay, so here's what we could say. No, I do not agree with Jack. Looking at the first three rows, the data does appear to be linear because the average rate of change is the same for intervals 5, 10, and 10, 15. However, after that, the average rate of change does not remain constant and it decreases for each successive interval. This indicates that a linear model is not appropriate for the data. Okay, so from here to here it went down 0.12, and then this was only 0.7, and so on and so on. And then it increased. Okay, page 4 brings us to part B of this problem, and it says to create a scatter plot of length versus oscillation time. All right, so I copied over the table from the prior page, so I don't have to keep going back and forth and back and forth and back and forth. All right, so we're going to create a scatter plot. So the first thing I want to do is have an x and y axis here, so I'll put that in. Okay, so here's my graph. I did an x-axis, and I did a y-axis. And this is 10, 20, 30, 40, 50, 60, 70, 80, 90, 100, 110, and then I went up. And since these are only going up to 2, every 5 is a time in seconds of 1 second. So this is a fifth of a second, or 20 seconds, or yeah, a fifth of a second, or 1/20th of a second. All right, so there's our graph. Length in centimeters, time in seconds. So make sure you label your x and y axes. Pause the video if you need to copy this. I'm going to continue now and plot the points. So 5, comma 0.45. 5 is here, and 0.5 is here, so 0.45 would be approximately there. 10, 60. 10, 0.5 is here, so 0.6 would be up a little bit higher, maybe there. And then 15.75, so 15 is here, 0.75, 3/4 of the way up, approximately here. Let's see, 20.88. That was 15. Let me move that over just a little bit. So this should be like here. And then 20 was 0.88 up here. And this might be up just a hair. Put that there. So this is a little tricky. Small graph. All right, so 0.25 was 1. So 10, 20, 25 is here, and that was right here. And I'm thinking 0.88 should be up a little bit, like right here. Again, this is very difficult to graph. All right, it's kind of looking linear so far. They're so close together. So 25, 1, 31.07. So 31.07 would only be, whoops, let's see, 31.07. Well, this is 2, 1.5, 1.2. 1.07 is really close to 1, so down here. 50, 1.42. This would be 1.5 here, so 1.42 might be about there. And then 75. Here's 80, here's 70. 75 is halfway between these two. And 1.75, about 3/4 of the way up. So here's 1, here's 2, 3/4 might be about here, and that is 0.75 right here. So you can see now that it's definitely not linear. It's coming up and then it's slowing. And then finally 100, which is here, almost to 1.98. So there is the graph of this function. Based on the scatter plot, what sort of function might you use in this data? And it could be a square root or maybe a cube root positive side. Okay, so it appears that the data could be modeling using a square root function or possibly a cube root function. Okay, part D. Mr. Williams, the science teacher, tells the students that the oscillation time for a pendulum can be found using the formula T equals 2 pi times the square root of capital L over 9.8, where L is the length of the pendulum in meters and T is the oscillation time in seconds. Does this formula support the results from the table? Explain. Okay, so what we can do here is use our calculators. And the way I would do it is I would go to y equals and clear everything out of there. and put this function in terms of y. So t is my y. Y equals 2 pi times the square root of L, that's where our x will go, x will be our L, divided by 9.8. Okay, so if I hit graph, and I want to do a window from time in seconds, x is 5 to 100, so window, I would change my x minimum to 0, and my x max to 100, and my y minimum 0.45 or 0 to 2. So now when I graph that, oops, what happened? Zero to 100 for x, 0 to 2, scale. Okay, the y scale's got to be way smaller. Let's try 0.1 for starters. That didn't work. Okay, let me see. How about zoom fit? Okay, that's better. Zoom fit. Alright, so I'm curious now what my window is. 0 to 100 and 0 to 20 with a scale of 0.1. Okay, so there's our zoom fit. There's our graph. And it does look like this right here. Alright, so now what it's saying is, does this appear to be the function for these points? So now I can look at my table. And I can plug values in that I have. So I have 5. And I have 10. And 15. 20. 25, 30, 50, 75, and 100. Okay. Two pi times the square root of x divided by 9.8, where L is the length. Does this formula support the results from your table? Explain. Okay, so what's going on here is, if you read the directions, it says the length of the pendulum is in meters. L. Formula is T equals. So this is T time, and this is L length. L is in meters. Well, this is in centimeters. So there are 100 centimeters in a meter. So if I plug those values into my calculator, 5 centimeters is not 5. It is 0.05. So let me clear these. So you always have to read, and if something doesn't make sense, try to figure it out. So what happens if I put 0.05 in? And look at that, 0.448 is really close to 0.45. So 0.1 enter, 0.15, 0.2, 0.25, 0.3, 0.5, 0.75, 0.100, or 0.1. Okay, or is that just 1? Yes, just 1. 0.25, 0.3. Okay, so there was enough room. But anyway, 0.456, 0.77 is close to 0.75, 0.88, 0.897, 1, 1, 1.07, 1.09, and then finally all the way down to 1. It skipped because it only shows so many. 1 was 2.0071, and 100 was 1.98. So that is very close. So yes, that would be a good representation of this data. Part E says, looking at the table of values, what effect does quadrupling the length of the pendulum have on oscillation time? Use the formula from Part T to demonstrate why this is the case. So if we're going to use this formula, we're going to use the formula t equals 2 pi square root of L over 9.8. All right, so if we're going to quadruple the length, that would be making that 4 times the length, 4L. So there's our equation we're going to use. Okay, quadrupling means multiplying by 4, so it's going to be 4L divided by 0.98 in our equation. So that's going to equal 2 pi times the square root, and let's see. Okay, so what we're going to do is, in general, we are going to determine what quadrupling does. So 2 pi is 2 pi. This 4 can come out in front like so, leaving my function the way it was with the 4 in front, right? Okay, and that is going to equal 2 pi. And then I can split up square roots when I have multiplication. So this could be times the square root of 4 times the square root of L over 9.8. But the square root of 4 is 2. So that's going to equal 2, and then times the 2 pi. So I took the square root of 4, which is 2, and I just brought it down in front. And then 2 pi times the square root of L over 9.8. So now I have the function 2 pi, and the original was right here, and that's still right here. So quadrupling the length of the pendulum did what to the length of time? On the time? Well, it doubles it. So quadrupling the length of the pendulum doubles the time, because our function is still the same as it was here, but it's being multiplied by 2. Okay, page 5 brings us to question 3. The growth of a Great Dane puppy can be represented by the graph below, where Y represents shoulder height in inches and X represents the puppy's age in months. So here's a little blue Merle Great Dane puppy, and there's a blue Merle Great Dane adult. I have had Great Danes in the past, and one of them I had was a blue Merle, so here's a couple of pictures. All right, so anywho, the growth in inches. Okay, so the time in months since birth, 0 to 40 months, 3 years, 6 months, and height in inches. The shoulder height started out around 12 inches, a foot. So this little guy is about a foot tall at the shoulder. Okay, at birth, I guess, 0. The growth of a lion cub can be modeled by the function represented in this table below. 0 months, 8 inches, and so forth. Which animal has a greater shoulder height at birth? All right, well, shoulder height at birth of the lion cub at birth was 8 inches. The shoulder height of the Great Dane puppy at birth was, here's 8 down here. It's closer to 13, I would say. Which animal has a greater shoulder height at birth? The Great Dane puppy. Okay. B, which animal will have a greater shoulder height at 3 years of age? That's 36 months. So 32, 34, 36 is right here. So I like to, in my graph anyway, since I can do this, I like to draw a segment straight up from there over to there, and then see what that height is over here. It's very accurate when I do this, as long as I can do it. Right there. And so, as you can see in the graph, the Great Dane puppy at 36 months is just over 24 inches in height. And the, let's see, lion at 36 months, well, this is at 32, is 23.8. So at 32, it was 23.8. It was almost the same. Okay, so the lion's shoulder height at 36 months, 20, 22, 23.8. At 36, it's approaching 24. It'd be over 24, so I'd say approximately 25 inches, maybe. Okay. Looking at the table of values, the average rate of change for each interval is decreasing. Okay, this is going from 8 to 8. That was 10. This was only 2.599, and this was less than that, and this was even less. This was 1.4 approximately. So it's decreasing, so the growth rate decreases. So on the interval 24 to 32, the change is 1.452, right? Just subtracting. So on interval 32 to 36, the average rate of change should be less than 0.7. So less than 0.7. Therefore, if I increase this by less than 0.7, say 0.6, that would not be 25. It would be 23.8 plus 0.7, which would be 24.5. 24.574 approximately, right? The Great Dane's height at 36, as we see in the graph, is a little bit more than 24 as well. So 24 and a half would be up higher. So I would say the lion would have a higher shoulder height. 24.574. This is not 24.5. 24.5 would be up a little higher. Okay, but it's really close. It's hard to determine exactly. Now part C says, if you were told that the domain for these functions is the set of all real numbers, would you agree? Okay? No, the domain is your x. All reals is positive and negative numbers. You can't have negative age. Okay? So a puppy's born, it is 0 months old. Before it's born, you can't measure its shoulder height, especially before it's conceived. So there are definitely limitations on the domain. So how could we word this? Okay, so how's this? There are physical limitations on time and height. So the domain must be greater than or equal to 0, but must not exceed the finite limit of their lifespan. So Great Danes live 8-9 years. I had one that lived to be 11 or 12, but that's pushing it. And let's see, it says, and the range must both be greater than or equal to the finite heights recorded at birth, and less than or equal to their maximum possible heights. Both the domain and range may have other limitations as well. For example, neither animal will grow continuously for its lifetime. Rather, both are likely to shrink if they live to an old age. Okay, page 6 brings us to the end of lesson 22. Review the lesson summary and go to your problem set.